Hi, in this video we're going to talk a little bit about rods and cones and how the adaptation changes in different parts of the eye and what impact that has on vision. So the first thing to understand is that we have two kinds of photoreceptors in the eye, rods and cones. Now where these are primarily located differs between both of them. The cones are primarily found in an area of the retina called the fovea. It is a relatively kind of small area. The cones are found on the periphery, outside that. Now it's also important to understand that we have an area called the optic disc, or the blind spot. In that area, nothing is found, as the nerve is leaving the eye at that point. So the other thing is that rods and cones have different wavelengths they're sensitive to. So cones have three different sensitivity ranges, and rods only have one. And that is because they have three different opsin proteins and they only have one different opsin protein. And it's really that the opsin which helps determine how sensitive it is to a specific range of light. So that basically means that explains why in cones that's typically where acuity is the greatest. We'll talk a bit about how detail is greatest in the cones, but also this allows us to see color much easier in this region, and typically color is associated with the fovea of the eye because the different opsins allow us to detect different ranges of colors and vision. In terms of sensitivity to light, really the cones have a really poor sensitivity to light, which means that in darkness these are very poor, and rods are quite good in darkness because they have a relatively good sensitivity to light. And what that basically means is that rods are not going to break down cGMP as quickly as cones will. When cones break down cGMP, automatically you basically will have a huge breakdown in breakdown to GMP, and you'll have all those channels unlocked. Rods do it much more slowly. So that's why daylight vision usually occurs in cones, and rods are very much better in darkness. In terms of the recovery rate is much faster in cones, which means that they can detect fast moving changes. If you see like something jump out in front of you, it will primarily be the cones that assist you with that, and these are much slower. Okay, so then let's have a look at like where these are distributed. So I'll just clean this up. So basically, if you think about where they're sort of laid out in the eye, it kind of looks a little bit like this. You have the center of the eye here, and in the center, you have, for a small region, you have the cones, and for a further region, you have the rods. They're sort of on the periphery, but it's also important to understand is that the further you go out, the less rods there are too. And there is a point, maybe I should draw this a little bit more like this. There's a point of crossover, but you'll notice here there's nothing. And this is the blind spot, or the optic disc. Okay? And so basically, this sort of explains why you won't see anything there. But the main thing to understand are cones are primarily in a small area called the fovea, and rods are primarily on the outside of the periphery of the eye. Now, the other thing to think about is that the different axes of light coming in. So let's imagine we have an eye here. Light on what we call the principal axis, so the straightest axis, will primarily hit the fovea. However, light on other axes will primarily hit the rods. And that's why when we gaze at something, when we change, like why do we look? Why don't we just observe things? Why do we move our head to look at things? The primary reason is to get the principal ray, actually the principal light rays hitting the fovea where visual acuity is the greatest, rather than on the rods. Okay, so the next thing we've talked a little bit about previously, and we'll just recap it, is the idea that you have different opsins for different kinds of receptors. So as we know, the opsin is the protein part, and they, in the retina they have a retinal which attaches to the opsin. Say we'll click in here, it'll be a perfect fit, it'll click in there, and in the rods this is called 11 cis retinal. Now it's important to understand, like I said before, rods only have one protein opsin. Okay, so they can only detect one wavelength of light. However, interestingly, cones have 3 different opsins. Okay, and so they're able to detect a larger wavelength, and not only larger but different wavelengths, so they'll be able to differentiate between colors. And that's why when you look at something, it'll look, the range will look roughly something like this, where you have rods can detect this frequency, that's rods, and usually that will be somewhere between 400 to 600 nanometers is the wavelength. But then you'll have cones being able to detect a blue wavelength that might go somewhere like this, and then they will also be able to detect a green wavelength, which will look a little bit more, I've done green twice, but you'll be able to see this, something like that. And then they'll have a red wavelength that maybe go all the way to 700. And this is not an exact graph by any means, but the point I'm trying to point out here is that because these have different opsins, you have 4 different opsins between the rods and the cones, you're going to have different wavelengths which are easiest to detect. So for instance, the blue wavelength from the cones, that will really specialize in detecting blue light. And the green wavelength, that will really specialize from the green cone, will specialize in green lights. And because of this is really how we're able to differentiate between colors, and why the cones play such a really important part in that process. So let's talk a little bit to summarize another point, which is rods are more sensitive to light than cones. So what this basically means is that rods are more sensitive to light than cones because they contain more photopigment and because the light activated enzyme cascade in rods is more efficient than in cones. So basically, rods also have to pay a price for this greater sensitivity because they're almost completely non-functional in daylight. So in other words, because rods typically work at nighttime, a little bit of light hitting the rhodopsin molecule has a big impact on creating, breaking down cGMP into GMP and hyperizing the cell really quick. And so rods, because a little bit of light can have such a big impact in rods, they're almost completely useless during the day. However, cones are completely different. Cones are less effective than rods, and they recover sensitivity easier. So what that basically means is they have a more efficient light adaptation process, in that when the way a cone will work is that when we've talked a little about this previously in other videos, where if you don't have cyclic GMP opening, then all of a sudden you will have the ability to for the GC protein to come along, and because there'll be no calcium entering into the cell, all of a sudden this will be uninhibited, and you'll be able to produce more GMP through to cGMP, and that process occurs all over again, which is why they're able to recover a lot faster. Now, remember, both rods and cones recover sensitivity in the dark. So what that basically means is that, rods and cones will be able to... Okay, I want to really show you guys a little bit about the rods and the cones and where they are found. So, obviously we talked about this before, but I'll just recap. In the retina, there's an area called the fovea. The fovea is where you find mostly cones, okay? And outside that area, there's more rods. Now I've drawn a diagram, a really sort of terrible diagram, but hopefully it helps. And you'll be able to see that in the periphery, you'll see a lot more rods. Now it's important to understand that the further you go out, there isn't more rods. They're still greatest in number just outside the periphery. However, the further you go out, there's virtually no cones. Virtually all the cones are based in the fovea. Now there's a gap here, you'll be able to see a gap here, and that is because we have a blind spot there. And the blind spot is usually on one side of the fovea, though it can move around a little bit, and that is blocked because of the optic disc, and there's no photoreceptors in other parts of that. So the other important concept to understand is that one of the reasons why we move our heads when we look at something, why don't we just stay focused and just look straight and observe things on our sides, etc., is because we'll be able to get the greatest amount of acuity if we land something on our fovea. And we'll talk a little bit about why in a minute the fovea is a better place to get acuity, but just trust me on that for now. But this is called the principal axis. And this light, if we move our eyes and move our head around so that the primary light is hitting the fovea, we'll get the biggest acuity. These other axes will land on rods. Now, it's important to understand the acuity there, and what we'll see is much less on the outside. We'll talk about why rods have less acuity in a moment, but that's really why we move our heads around, so we can look at something and glance at something. So let's look at why that is. So you probably have seen this diagram before. This part in yellow here is the opsin, and this is the retinal part, the photopigment up the top here, and they're attached together. Now, it's really important to understand it is the opsin which determines the wavelength that is detected by that photopigment. So in cones, we have 3 different kinds of opsin, whereas in rods, we only have 1. And if you've watched other videos, you'll know that in rods, this thing here is called rhodopsin. However, rhodopsin is not the photopigment that's going to be used in cones. That's different. And how does this kind of look like? Well, you'll be able to see here that, and I'll change the color here to make it a little bit clearer, but each of these will have a different range. So you'll be able to see, cones will be able to detect in this range here. Just highlight. Cones will be able to see this. You'll have green cones that can detect this. You'll also have rods that can really stay in this medium area. But then you'll also have red cones that can detect light in between this range. And because of that, you have 4 different sorts of wavelengths that allow us to detect different degrees of color. And why do you want that? Well, it's basically if you didn't have that, all light would look the same, and you would essentially be colorblind. And people that are colorblind really suffer from issues in the fovea where they don't have different wavelengths available for various reasons. So one of the other things that gives diversity to vision is this idea of a receptive field. Now, I want you to think about receptive fields, and I'll explain what they are in a second, but just know there is a direct pathway and an indirect pathway. So hopefully by now you should know that at the retina, the rods and the cones are actually not sitting on the retina. They're the furthest back. So in the direct pathway, we basically have got the ganglionic cells up the front here. We then have a bipolar cell, just sort of the intermediate cell. And then at the back, we have the rods or the cones. This looks something roughly like that, right? The direct pathway is what I just described to you. This is the direct pathway. And it makes sense. If something's going to activate it, it activates these direct pathways. However, the vision also needs something that is, and let's say for instance, this is the receptive field. Vision also needs context. So imagine we start using the inputs of these to the neurons as well. So we don't just use the direct pathway, but we also use these alternative pathways. And we call these amacrine and horizontal cells. And the amacrine and the horizontal cells do not touch or do not connect. There's no connections between these at the top, but they connect together through to the neuron back here through an indirect pathway. And they kind of give context, and we'll explain what that context looks like. But just to imagine it, you've got the direct pathway where the light has directly hit the receptors. It's obviously, traveled through ganglion cells and the bipolar cells and through the rods and cones into the neurons. And then it contributes part of the field. But the field for that neuron is greater because it gets context, and what it can see gets that context from the indirect pathway as well. And if you start thinking about receptive fields as having two parts, and a field is simply almost, if you think about it, of what a neuron can see, it kind of looks a little bit like this. You have the center, which we call the concentric receptive field. The center is all of the direct pathways, and the surround comes from these indirect pathways up here. And it kind of looks a little bit like an egg. But once you understand that a surround has a center and a surround receptive field, and there's a concentric receptive field and the surround receptive field, and it looks a little bit like an egg, it's also important to understand the size of these surrounds matters. So in a fovea, in the cones, the receptive fields are very small. So they look really small and they look a little bit like this. In the periphery, they're really big. They have a lot of input and a lot of information. And if you were to ask which of these is the best at seeing vision, and seeing it's not just vision, but higher amounts of detail, the smaller the field is, the more detail, right? It's kind of like if you zoom in a lot of detail, like if you're using a microscope and you zoom in, you'll only be able to see a little bit, but you'll be able to see a lot in that little bit. Versus if you are using a microscope and you zoom out, you'll be able to see a lot, but not a lot of detail. And both of those are important. But what we find is the smallest receptive fields exist in the fovea, in the cones. And the biggest exist further out in the periphery. The size is bigger the further you go out. And of course, we have a blind spot where there's nothing. So that's really important to understand. However, that visual acuity is completely different during the day because, as we talked about previously, cones aren't able to show us anything at night time because their adaptation rates are too fast for CGMP. What ends up happening is that you'll have the greatest amount of acuity in the rods and a small amount in the fovea, and it's got nothing to do with the size, because remember we've talked about obviously the fovea and the cones have a smaller retina, but when they are not online and they're not working properly, then the rods take over. That's why night vision primarily happens in the rods. But then there's also this idea of indirect and direct pathways. And a lot of the time, these processes are excitatory or inhibitory. So let's say we have a bit of light, and that light shone on the middle. That might be excitatory, meaning that it maybe hyperpolarizes a cell and it increases the chance of an action potential happening. And this, the surround, if the center is excitatory, this will be inhibitory. Now, the other thing is that it's not just that way. I mean, the center could be inhibitory, and the outside could be excitatory. And this is, if the center is excitatory, it's called an on center. If the center is inhibitory, it's called an off center surround. So let's also think about how else this sort of surround concept can be used, and it can be used for colors. Let's say, for instance, in the red-green system, when light is shone on a red center, red is shown. When light is shone on a green surround, green is shown. Now, it's also important to understand there are examples of this where it's the exact opposite, where green is the center and red is the surround. So these red-green systems exist in the body, and there's also yellow-blue systems as well. And the point is that this excitatory inhibitory system exists in both exists throughout the retina, and it also helps us detect color, perception. It also helps us tell context, and it's always driven by this idea of the direct and indirect pathways and the impact they have on that system. Okay, that's all for this video. Thanks.